Hello, this is my rotational motion screencast, and I will be reviewing problem 2.2. So in problem 2.7, the prompt is, you are helping to design a new fire escape for your third floor apartment. You step out of the window onto a crossbar that is attached to a rope, which in turn is wound around a massive solid cylindrical flywheel that can turn on its axis. As you fall at increasing speed, the rope causes the flywheel to turn at an increasing angular velocity. Your task is to choose a flywheel that will enable you to move at a safe 2 meters per second when you reach the ground 10 meters below your starting position. Your mass is 80 kilograms. Determine the rotational inertia and the mass of the uniform 0.8 meter radius flywheel you need to buy. So here's the sketch of the diagram of the problem. So over here you can see that the pulley with 0.8 meters of radius and the crossbar, which has a total mass of 80 kilograms. Its starting velocity is 0, of course, and the total distance from the ground is 10 meters. And then at the velocity final is 2 meters per second. I set the 80 kilograms as m and the 0.8 meters as r. And of course, the delta x is 0 at that point. The force and torque diagrams. So first we establish what's positive, and in our torque it's counterclockwise, and in our force diagrams it's up and to the right is positive. So over here there's two force diagrams. So the first is the force opposing the movement downwards, which is going to be equal to the tension force caused by the pulley. And then the second, when the system is set as the 80 kilogram crossbar in the person, the force downwards is Fg, and the force upwards is the tension, which is basically the force opposing it. And in this diagram, you can see that the force downward is greater than the force upwards, which is causing an imbalance, which is going to cause some acceleration of the system. So now we get to our equations and propagations. So the sum of the torques is just going to be the tension times the radius, and from that you can start manipulating to solve for t. So alpha is going to equal the sum of the torques over I, and it's also equal to a over r by its definition. So once you start propagating, you get that tr squared, once you multiply this to the other side, over I equals a. And then when you solve for just the tension, you multiply both sides by I and divide by r squared, so you get t equals ai over r squared. Now from our basic kinematics, you get A equals force of gravity minus tension over m, and which is just the sum of the forces over m. And that would give you mg minus t over m. But over here we had t as a I over r squared. And once you simplify that, you get mg minus ai over r squared over m, and then you can simplify that further to just mg over m plus I over r squared. Then when you get to the final steps, you have mg over m plus ir squared, which is what you got for acceleration over here, is going to equal v finaled over 2 delta x, which is just another kinematics equation. And when you multiply both sides by, or when you divide both sides by, or sorry, when you take the inverse of both sides, you get m plus I over r squared equals 2 delta x over v final squared. And then you multiply both sides by mg to get m plus I over r squared equals 2 delta x mg over v final squared. Finally, you subtract m from both sides, you get I over r squared equals 2 delta x mg over v final squared minus m. And then, since it's a cylindrical flywheel, your equation for moment of inertia is going to be 1/2 uppercase m r squared, and then the r squares cancel out, so you just get uppercase m over 2. And then finally you get that as equal to this equation. So once you multiply both sides by 2, you get the equation for the mass of the flywheel. And now we just need to plug in our the variables that we know already. So we have R is 0.8 meters, V final as 2 meters per second, G as 9.8 meters per second squared, M as 8 kilograms, and delta X as M. So you get M equals 7,680 kilograms, and I, which is you just plug in once more 1/2 mr squared to get 2,457.6 kilograms times meter squared. And that is how you solve for the mass and the moment of inertia of the cylindrical flywheel.